So far, we've used the substitution rule from integration to find solutions to our differential equations. The differential equations that we studied were linear, first order because they only went up to the first derivative, and had constant coefficients. We will next look at solving linear first order differential equations where the coefficients are not necessarily constant, and we'll need some new tricks. Since a differential equation must be linear in y to be a linear differential equation, our generic way of writing a linear first order differential equation is dy dt plus some function p of t times y is equal to another function of t, g of t. But I again want to stress that we have no conditions on the functions p of t and g of t in order for us to call the differential equation linear. In our next method, for solving linear first-order differential equations, we will need another rule from calculus. We're going to need to look at the product rule. So recall from Calc 1, the product rule says that if we take the derivative of the product of two functions, mu of t times y of t, it can be rewritten as mu of t times dy dt plus d mu dt times y. The first times the derivative of the second plus the derivative of the first times the second. In order to line up our linear differential equation in standard form with the product rule, we're going to multiply by a function mu of t. This will give us mu of t times dy dt plus mu of t times p of t times y of t is equal to mu of t times g of t. Just multiplying each term in our standard form by mu of t. Now, notice the similarities between the expression on the left-hand side of this equation and on the right-hand side of the product rule. In both, we have mu of t times dy dt as our first term, followed by some function of t times y. The difference here is that in the product rule, we have d mu dt as our function being multiplied by y of t, and in our other equation, we have mu of t times p of t as the function of t that's a coefficient of y of t. So as long as these expressions are the same, that is d mu dt is equal to mu of t times p of t, the right-hand side of the product rule is equal to the left-hand side of our equation above. So we can conclude that the derivative of mu of t times y of t, which is equal to mu of t times dy dt plus d mu dt times y of t by the product rule, is equal to mu of t times dy dt plus mu of t times p of t times y of t, so long as d mu dt is equal to mu times p, which is equal to mu of t times g of t from our linear differential equation. Now, this process raises a couple questions. For one, how do we find such a mu of t? And so what if it's true? So what if these two things are equal? But notice we have a condition on mu of t. In particular, we need d mu dt to equal mu of t times p of t. So we can find mu by solving this differential equation of mu, which we can do by dividing by 1 over mu on both sides. So we have 1 over mu times d mu dt is equal to p of t, which can be solved by integrating both sides, and on the left using the substitution rule as we did before. So we have the integral of 1 over mu d mu is equal to the integral of p of t dt. And the integral of 1 over mu d mu is the natural log of the absolute value of mu. So exponentiating both sides gives mu of t is equal to e to the integral of p of t dt. While it's a little bit of a messy formula, it gives us a way to find mu of t to ensure that the equation above is true. But we still need to answer, why is this useful if it is true? To see why this is useful, notice that if we pick mu of t in such a way, then the derivative of mu times y is equal to mu times g of t. So integrating the left-hand side will undo the derivative to help us solve for y. So if we integrate both sides, we'll have the integral of the derivative of mu times y is equal to the integral of mu times g. And from the fundamental theorem of calculus, the left-hand side is just mu times y. And since we're trying to find the function y of t that solves our differential equation, all that's left to do to find y is to divide by mu. So we can conclude that our solution y of t is equal to 1 over mu times the integral of mu of t times g of t dt, so long as we pick mu of t to be e to the integral of p of t dt. So this formula gives us a way to find a solution of any first-order linear differential equation that we write in standard form above. All we need to do is be able to compute those two integrals, and then we can find a solution.